In this video, I've presented a work-along roadmap problem. Feel free to pause the video and try to solve this roadmap yourself. Remember that the goal of this roadmap is very ABC reaction focused. I don't need mechanisms here, I just need the boxes filled in. It's basically a series of ABC questions. When you're done, I'll work through together and we can see how correct you were, and I'll show you my thinking on how to approach these problems. Hopefully now you've had some time to look at this problem. Let's zoom in and start from the top. And really, this whole roadmap begins with naked, empty benzene. Let's go to the right first, and here we can see that a methyl group is being added to the benzene. Since we're adding directly to the benzene, that tells us that we're doing an EAS reaction, and we need to figure out which one it is. Since the methyl group is an alkyl group, it's got to be the Friedel-Crafts alkylation. To do the Friedel-Crafts alkylation, we need FeBr3 or AlCl3, some sort of Lewis acid catalyst, along with the group that we want, the methyl group, connected to a bromine. Remember that if you use chlorine, you can use AlCl3 instead. I have seen them mix and matched. It shouldn't be important. What matters is that you have a Lewis acid catalyst. Great. Hopefully you got that box right. Now we can continue along from the toluene. Now, two different options were presented here. One uses HNO3 and sulfuric acid. And if you remember, these are the conditions for the nitration of benzene. This is another EAS reaction. Now, before, we didn't need to worry about where we were putting this methyl group. But now that we have a methyl group, we have to worry about where that nitro group is going to go. Remember that while we are adding a nitro group, it doesn't matter, right? The group that we're adding isn't going to tell us where it goes. We have to look at the parent group. The parent group is a methyl group, which is a weakly activating substituent. It's going to be an ortho-para director. So ortho or para is the best place to put this nitro group. Oh, that's meta, ortho and para. There we go, ortho, para. And we're going to put it para because it's further away. It's better sterically. Again, putting it ortho wouldn't be incorrect necessarily, but putting it meta would be. Remember that the nitro group can just be drawn as NO2. Awesome. Right. Now we can continue on with this path, may as well, and see what happens. So here, this is an ABC question with B taken away, one of the harder questions. We see a nitro group and a methyl group in our starting material, and in the product, we haven't added anything to benzene, but the NO2 group has changed into an NH2 group. You may recognize this reaction, but recall that filling in these boxes can be harder and requires a little bit of memorization of what those reagents are. Again, there was no mechanism for this, so it's not even like you can understand this mechanistically. Now, of course, there is a mechanism, but it's typically not tested. This reaction is going to be the Clemenson. The Clemenson uses zinc, mercury amalgam, and hydrochloric acid. By using the Clemenson, we can reduce the nitro group into the amine and have now it's a strong activating group. One more reaction in this chain. We are now going to use a sulfo, so a SO3, an acid. This is the reactions for the sulfation of benzene. Now we have to ask, well, we have multiple substituents, where are we going to put it? Not only do we need to find what the activating and deactivating groups are, but we need to figure out which one we're listening to. Here we have a weakly activating methyl group and a strongly activating nitrogen. Remember that it has the lone pair there. It's a strong activator, meaning that we're only going to listen to the nitrogen. The nitrogen says that it wants ortho and para. It told me itself. Now the para position is taken. That means that the next group is going to be preferred on the ortho positions relative to the group that we care about. So left or right doesn't matter, but it would be wrong to put them on those positions. Right, we're going to put that sulfo group here. That would be incorrect. Right, we're going to put it here. And there we go. Starting from naked benzene, following this pathway, we were able to make this tri-substituted benzene. Clearly, while benzene isn't very reactive, we found ways to make it do what we want. Going back up to the toluene, let's take a look at this other path. So here, KMNO4 was used, and in the presence of heat. Now, KMnO4 isn't a reactant for an EAS reaction. KMnO4 is a strong oxidizer. If you're curious, we'll be learning much more about this in section 6. But what it does to a toluene is that it oxidizes and replaces these hydrogens with oxygens, if you recall, leading to the formation of a carboxylic acid. Now, we can't add carboxylic acids to benzenes using EAS reactions, which is why this is such a useful tool. Now that we have benzoic acid, right, pay attention, that weakly activating group has now turned into a strong deactivator. Let's continue on. Using benzoic acid, the reactants are given as chlorine and AlCl3. You may recognize these reagents as the reagents of the halogenation reaction for benzene. This is an EAS reaction, and we're going to be adding a chlorine to the product. Of course, the question remains, where am I going to put the chlorine? And to understand that, remember, we don't look at the chlorine. We understand that this is the only group. It's deactivating, it's meta-directing, and therefore we need to put that chlorine on either one of the meta positions. Great. So now we have our di-substituted benzene, and now we're going to use methylbromine and FeBr3. We used those previously above. This is the alkylation of benzene, so it's another EAS reaction. But now the question is going to be even harder. Where do we put that methyl group? So drawing the original structure, we can see that we have two directing groups now, and we need to find out which one we're going to listen to. The carboxylic acid is a strong deactivator, while the chlorine is a weak deactivator. Many people will get confused here, but remember that number line of activation. Technically, the chlorine is the strongest activator. In a sense, it's the least worst. So we're going to listen to the chlorine. Now, chlorine, despite being a deactivator, is an ortho-para director, which means our positions that are open are here, here, and here. This is a good example of how ortho and para selectivity changes on a di-substituted ring. Typically, we have this idea that para is better. And the para position is fine here, right? But so is this one. They're both connected to one nearby group. The worst position is actually this one, since it's in between both substituents. That's how we can interpret sterics when it comes to ortho-para substitution. So as long as you put the methyl group on one of those two positions, you'll have a correct answer. Awesome. That wraps up this wing of the roadmap. Lots of different reactions, lots of different benzene types of chemistry. We only have one pathway left to go. So here we can see that we have a benzene ring, and we're adding this whole group. And this is where many students will get confused, especially in these larger questions. But don't focus so much on the big group, and focus on what was connected to the benzene. We can see that this is definitely an acyl group. In a sense, I could draw it as R. Right? The first thing connected here is a carbon. Who cares what this is? So what is R then? Well, it's going to be everything that's connected here. It's the Friedel-Crafts acylation. So what we're going to do is, of course, we need the Lewis acid catalyst. We'll take our acyl halide and then just connect it to whatever we see over here, which is carbon, and then another acyl bromide. In a sense, this chemical has two acyl bromides on it, and one of them is going to be used, either one, to perform the Friedel-Crafts acylation. Now that we have this chemical, right, I'll leave that up there. Now that we have this chemical, all we need is FeBr3 for this product to form. Right, now FeBr3 was already there, so in a sense you could have just let this reaction continue, but I like to separate the steps to really show this. What's going to happen here is actually an intramolecular Friedel-Crafts acylation within the same molecule. A rule that I'm going to cover, I may have already covered it, and I'll cover it again, is that whenever you think a ring is forming, always make sure you number your carbons. That'll help you make sure you don't add or drop them, as it can be very easy to add and drop carbons by accident. So what's going to happen here, we can imagine, is that the benzene is going to once again do the Friedel-Crafts acylation. except now instead of attacking another molecule, it's going to attack itself on carbon 4. Now again, this is an oversimplified mechanism. We know the full mechanism is going to involve activation of that acyl halide into the acylium ion, but clearly the idea is that this carbon here is going to form a bond to carbon 4. So let's see what that might look like. Carbon 1 is still going to be connected here, but this red carbon here that I've labeled, is now going to be connected to carbon 4. And it is the Friedel-Crafts acylation, so carbon 4 will be a carbonyl. Now, this is where the numbering comes in handy. 1 is connected to 2 and connected to 3, which is connected to 4. There's no arrows in any of this mechanism that's going to affect carbon 2 and 3. Really, they're just going to come along for the ride. Here's carbon 2 and here's carbon 3. And you can see that we've actually formed a ring on the benzene. In totality, that's the work-along roadmap. I hope you found this useful. Other than the roadmap question, we also have synthesis-type questions. They're also based on the ABCs, but they require you to think about the order of operations and how we're going to get a multi-substituted product like this, thinking just from the benzene. I'll see you in the next video to do some work-along synthesis problems.